Okay, more section 1.4. Looking for discontinuities. Pretty much, since our functions that we tend to deal with, our functions are usually fine. Look for problem points. Okay, so what the heck do I mean by that? Well, again, graphically, as long as it's not a removable discontinuity, we're probably going to see it just fine. But if it's a removable discontinuity, we could have some trouble. So algebraically, what kinds of things do I look for? Well, okay, what are problem points? Well, I'm going to use square root, but it's really any even root, but the square root of a negative. That's a problem, so that's one thing I might look for. Divide by 0. That's another thing I look for. And then piecewise transitions. So if I have a piecewise function, I might look there as well. So so typically, right, f of x equal x cubed, right? That's fantastic. That's great. Continuous everywhere. Why? It's a polynomial. But if I looked at, say, f of the square root of x, which is square root of x cubed, or just the power function x to the 3/2, all of a sudden here I think, wait a minute, we could have a problem because I can't take the square root of a negative number, and so in this case we would have, suppose I call it g of x equal x to the 3/2. That one's continuous for x greater than 0. Now notice I didn't say equal 0, even though it's defined there, but because I don't have a two-sided limit there. And now you could talk about it being being continuous on the closed half plane, as we would call it, because it's half the number line, or half line, I suppose. If we're just going to say continuity in general, I'll use the open interval from 0 out to infinity. Okay, so I could write it that way, or I could write it that way. Either one. Again, divide by 0. You have something like f of x equals, x squared minus 1 over x plus 1. Now this would be really tough on a graph because we've got a removable singularity here, right? Notice I have that x equals -1 makes me divide by 0. Now, like I say, if you were to graph this in something like Desmos, just visually, you would not see that, you know, what we have is this situation, and so this is continuous everywhere except x equal -1. But even at x equal -1, I have a removable singularity. So here f of x is continuous everywhere except x equal -1. And so what you might write is sort of the negation of that is you might write x not equal to -1 and say, oh yeah, it's continuous everywhere else. Okay. Now, just to point out that if I define then g of x equal x squared minus 1 over x plus 1 when x is not equal to 0, but then I defined it as -2, oh, not equal to 0, sorry, x not equal to -1, and then I defined it as -2 when x is equal to -1, now all of a sudden g of x continuous for all real numbers, because I removed that discontinuity or singularity, we could also call it. I removed it. Okay, so you know, there's the divide by 0 thing. Now you could also have the piecewise function, you know, so suppose I have f of x equal x squared when x is less than or equal to 0, and x plus 1 when x is greater than 0. Then, you know, everywhere except 0, this is going to be fine. Now the question is, well, what about at 0? Oops, I don't know what I just did. This is just, there we go. Okay. So, you know, this is just fine everywhere except possibly at 0. And the reason is x squared, I know that's normally continuous everywhere. I know that x plus 1 is normally continuous everywhere. So they're both fine on their respective intervals, but at that transition point of 0, I could have a problem. And so I just check it and I say, well, you know, what's the limit as x goes to 0 from the left of f of x? Well, that's the limit as x goes to 0 from the left of x squared. And, well, I can just plug that in and see that I get 0. But from the right, the limit as x goes to 0 from the right of f of x is the limit as x goes to 0 from the right of x plus 1, because that's what I'm using on that side of 0, and that equals 1, and oh, bummer, not equal. Oops. And so, in this case, f of x is continuous everywhere except 0. On the other hand, if I defined a g of x pretty much the same way, almost, x squared when x is less than or equal to 0, but then just x when x is greater than 0. In this case, g of x is continuous Okay, because I know x squared's fine everywhere except 0 for sure, and x is fine everywhere except 0 for sure. But at 0, then I'd need to check those two limits, but of course, you know, the limit as x goes to 0 from the left of x squared is equal to 0, but that's equal to the limit as x goes to 0 from the right of x. And so those are fine. Alrighty, so that's this idea of looking for discontinuities. You know, they're reasonably, in some ways, obvious. You know, square roots of negatives or fourth roots of negatives or something like that. You know, cube root of a negative is fine. You know, that kind of thing. Dividing by 0 is a problem. And piecewise transitions. So piecewise functions, again, typically the piecewise function is fine, you know, because it'll be a polynomial or an exponential or something like that on each piece. But then the question is, do they match up at the end points of those pieces? And oops, got my stylus there in the wrong spot. So, okay, so I think that's good for looking for discontinuities.